Okay, in module 2, the third theorem, we have totally 6 theorems. Okay, in that we have seen the Thevenin's and the Norton's theorem. Okay, so today we shall see the third theorem, that is superposition theorem. Okay, now one should understand not all the theorems are applicable to all the circuits. Everyone understand this point? Not all the theorems are applicable to all the circuits. For example, if you take Thevenin's and Norton's, which type of circuits we used to consider? We used to consider linear two-terminal networks. Okay, so you can obtain the Norton's equivalent network or the Thevenin's equivalent network across two open circuit terminals. So you need what? You need two terminal linear network there for Norton's and Thevenin's. Here what you need is different. Here you don't need linear two terminal network, but you need a linear circuit. Everybody understand? Linear circuit. Okay. What does that mean? Why the two terminal is not written here? Because there are no open circuit terminals here in this particular uh, theorem. Okay, the circuit for which this superposition theorem is applicable, there you don't need the two open circuit terminals as it was the case in Thevenin's and Norton's. Okay, so what is this particular theorem telling? In a linear circuit containing multiple independent sources. See here, if a linear circuit, it should be a linear circuit. There should not be two terminals open, is one condition. And that linear circuit should for sure contain multiple independent sources. Then only the superposition theorem is of use, otherwise it is not of use. Get that point? You should have a linear circuit. Along with that, you should have multiple, okay, two or more than two independent sources. The next question is, do you think there should not be any dependent sources? Yes, it can be there. Let's look into that later on. But as of now, understood, superposition theorem is applicable to a linear circuit consisting of multiple independent sources. Okay, so that's why, see here, this particular thing is highlighted, containing multiple independent sources. Okay, so in any linear circuit containing multiple independent sources, a current or a voltage at any point in the circuit can be calculated as algebraic sum of individual contributions of each source when acting alone. Algebraic sum of the individual contribution of each source. That means, suppose say there are two sources, one voltage source is there and one current source is there, suppose. Okay, and you're asked to find out a voltage or a current in some branch. Then what you will do, you can find out that current or voltage directly using mesh analysis or node analysis. But superposition theorem tells what? No, first see the contribution of just one source, keep it aside. See the contribution of another source, keep it aside. That means let not both the source act at the same time, is what superposition theorem is telling you. Just make one source act at a time, see its contribution, then deactivate it. Make another source active, see its individual contribution. Then after obtaining the individual contribution of each sources, okay, then add them algebraically. Okay, so then you will get what you want. Okay, so this is a different approach. We shall see, you'll understand this in a better way when we see the problems. Okay, so what should be the problem? What type of circuit should the problems be dealing with? They should be dealing with the linear circuits containing multiple independent sources. Fine, so let's move on. So superposition theorem is applicable only to circuits containing multiple independent sources. Very important thing. Not all the circuits are suitable. If you have just one independent source, it is not suitable. Can dependent source be present? Yes, as I've told you, they can be present. Okay, but we cannot deactivate them, is something that one needs to remember. We have to leave it to itself. That means we should not change it. Okay, so we have to leave it as it is if the dependent source is there. Okay, we'll solve such problems. Okay, I've got all the types of problems for you. Okay, we'll see one by one. Okay, very interesting stuff. Just concentrate, everybody. Yeah. First of all, is this a circuit with multiple independent sources? Yes, there are two. There can be two or more than two. There cannot be just one. Fine. So two independent sources are. That's why they're asking us to find out I naught by superposition theorem. Don't you think this I naught can be found out by mesh analysis? Yes, we can. Don't you think this I naught can be found out by node analysis? Yes, we can. We can even find out I naught by Thevenin's theorem. We can find I naught by Norton's theorem. How do we do it by Thevenin's and Norton's theorem? We remove this. We remove this 12 kilo because 12 kilo ohm is where I naught is flowing. And across the open circuit terminals, you find Thevenin's network or you find Norton's network and bring this 2 kilo ohm back at the end. So that is what we have done with finding out current or voltage using the Thevenin's and Norton's theorems. But here, for the first time, we're using superposition theorem. Okay, so I naught is what they've asked us to find out. So when I'm explaining, okay, it's good if you can copy down this network fast. Fine. So it has got two sources. One is the current source, other one is the voltage source, and all the resistors are 12 kilo ohms, and we are finding out I naught by superposition theorem. Get that? Now, what is the method? Okay, or what are the steps that we need to follow? Okay, is what I'm telling you now. Solution. Let I naught be I naught 1 and I naught 2. Why two sum of two currents? See here. We have I naught. Okay, this I naught can be taken as I naught 1 and I naught 2. Why just two currents? I naught 1 and I naught 2? Because we have just two sources here. If you have three sources, then I naught would be written as I naught 1 plus I naught 2 plus I naught 3. So number of independent sources would decide the number of individual contributions. So this is one individual contribution. This is another individual contribution. So if you add these individual contributions algebraically, then we get this. So we can find out I naught directly by mesh analysis or node analysis. But here, since they have asked us to find out through superposition theorem only, we have to represent our I naught as I naught 1 and I naught 2. So let's say this I naught 1 is the contribution of 6 volt source when acting alone. Okay, so this I naught 1 is the current that will flow in the circuit. Okay, when only 6 volt source is acting. So that means what? So that means only when this is acting, I naught 1 would be flowing here. So when this is acting, what should this be doing? This should be deactivated. How to deactivate this current source? By open circuiting. Everybody understand that? So when only 6 volts is acting, we need to deactivate. So that means you can open circuit this. Open circuit this and name it as I naught 1. Then what is I naught 2? I naught 2 is the contribution of 4 milliampere source when acting alone. When 4 milliampere source is acting alone, the contribution is I naught 2. See here? Let this be active. In the next case, let deactivate this. So when this is deactivated and when this is active, this I naught would be named as I naught 2 because it would be contribution of only 4 milliamperes. When 6 volts is not acting, it is deactivated. So that means we need to short this. I hope you understand this. Okay, that means we are breaking a big problem into many smaller problems. Find the solutions and bring all the solutions together to get the solution for the bigger problem. Everybody understand that? Even in your life, the things should go like that. If you have a big problem, see what is the cause for that problem. Okay, see if you can go to that root cause and try solving that before seeing the big problem ahead of you. Okay, so that is how even the life is. If you can break your problems into smaller ones, okay, solving a bigger problem is much tedious than solving the smaller problems. Okay, so this is similar to that. Okay, so we should understand it is I naught 1 and I naught 2 steps. Step 1, to find I naught 1, what we need to do? We need to find two currents now, I naught 1 and I naught 2. Fine. So what we should do to find out I naught 1, which is the contribution of 6 volts acting alone. So when 6 volts is acting, the other current source should be deactivated. Deactivating the 4 milliampere source, the circuit becomes, what does the circuit become? See here, it becomes this. Here there was a current source, okay, before deactivating. Now we have deactivated this. That means current has to be deactivated by open circuiting. Turning off or deactivation, they're all the same terms, okay, which we use interchangeably. Understand that? Okay, so that is gone now. It is deactivated, open circuited. Fine. Now, what is that we need to be careful about? Note the current I naught is replaced by I naught 1 because we are finding out I naught 1. Okay, so again, we should not be writing it as I naught. I naught is the combination of both 6 volts and 4 milliamperes acting together. But we need currents when each source is acting alone. Get that point? So that is why it is called as I naught 1 now. So find I naught 1. To find I naught 1, again it's the same. Okay, your theorems are more like practicing your mesh analysis and node analysis. Is it just that? But at the same time, see if you can think of some easier ways of dealing with the problem. Okay, instead of dealing with this as two mesh problem, see if you can bring the size of the circuit to be the smallest one. How is that? Since there is 12K and 12K, right? How these two are connected after removing 4 milliamperes, I'm saying. After removing 4 milliamperes, these two are how they are connected. They are connected in series. And this series combination is, see here, what would this series combination be? This series combination is in parallel with some resistor. Which resistor it is parallel with? See, this end is connected with this end of this 12K and the other end is connected with this end. That means they are holding hand to hand. So that means this 12K and this series combination are in series, are in parallel actually. This series combination and this 12 kilo are in parallel. So if you can look at such uh, things, minute things, which would bring huge difference in the solution. Okay, so it will make the solution very simple. Otherwise, it consumes time. Okay, so we should see to save a lot of time. So what we are doing is this 12K, 12K. Okay, they're not doing this. Not an efficient method. Not an efficient method to do this. Actually, you could have done that. So let us go the way it is prepared. Okay, but you should understand these two are in series. This series combination is in parallel with this. So you will have just one mesh. Get that point? Okay. Let's see how the things go. Two mesh, applying KVL to mesh one. How does it go? Plus 6, 12K into IA plus 12K into IA minus IB. Bring it to the standard form. I'm not spending much time on this. We have done that in detail with lot of classes spent on that. Okay. Now applying KVL to mesh 2. Okay. How does it look like? So it's minus 6. Okay. Plus 12K into IB minus IA plus 12K into IB plus 12K into IB. Bring it to the standard form. So you have two equations, two unknowns. Find those two unknowns. After finding out IA and IB, what would be your I naught 1? I naught 1 would be IA minus IB because IA is flowing in the direction of I naught 1 and IB is flowing opposite to the direction of I naught 1. See, where is IB flowing? IB is flowing everywhere here. IB is flowing everywhere here throughout this closed path. IA is flowing throughout this closed path. So when they are doing that, IA would be flowing in the direction of I naught 1 and IB would be flowing in the direction opposite to that. That's why I naught 1 is IA minus IB, and that happens to be 0.3 milliamps. It is becoming negative. Let it be negative. We'll consider the negative sign when we are adding the individual response. That is why the sum is called as algebraic sum. So algebraic sum of all the individual responses is what we are doing to get to the final answer. Okay, so this is one individual response, and this is the response of 6 volts acting alone. Fine. So let's go to step 2 to find out I naught 2, which is the contribution of 4 milliamperes source acting alone. Okay, for that, what we need to do? We need to deactivate 6 volt source. So deactivating 6 volts. How to deactivate 6 volt source? By short circuiting. So here was the 6 volt source. See, that is short circuited. And observe, this is now denoted as I naught 2. Is that okay with you, everybody? Fine. Now, what we need to do? We need to find out I naught 2. So node current I naught is now replaced by I naught 2. Very important, because otherwise you will keep searching for I naught 2 at the end. Okay, this is a super mesh problem. 3 meshes are there, but since there is a current source in between these 2 meshes, we can form a super mesh, and that is shown by the dotted path here. Let's mark the currents I1, I2, I3. We have to find the currents, the mesh currents. But after finding out mesh currents, what is I naught 2? I naught 2 is I1 minus I2. Understand that? So how many equations we need to find out the 3 unknowns? We need 3 equations. How would you get that? One equation by applying KVL to mesh 1. The other equation is by applying KVL to super mesh. Okay. And other equation is the constraint equation. So whether it is super mesh problem or super node problem, the very first thing that should come to your mind is writing the constraint equation. Get that? Okay. So it's a super mesh problem. Okay. Constraint equation is what we are writing. So it is I3 minus I2 is 4 milli. Applying KVL to super mesh. We have applied it. Okay. So in standard form, it looks like this. You can solve it with all the time. Okay. After this class or after you finish all your classes. Fine. Let's not again spend time for applying KVLs. Just get to know the concept. Okay. Solve it one by one. Okay. When the time permits. That does not mean that you should just leave it for your exam. No, the internals are approaching now. From 19th onwards, the internals are there. Okay. And all the syllabus is going to be there for that internal. So you need to be a little serious when it comes to learning all this. Fine. Okay. Another equation, we need 2 equations you've got, but there are 3 unknowns. So we need 3 equations. The third equation is obtained by applying the KVL to mesh 1. That is this. Everything is in detail. Okay, use it like a notes or whatever I'm sharing with you the video. You can just sit with that and learn things. Fine. So I1, I2, I3 can be found out. After finding out I1, I2, I3, what is I naught 2? I naught 2, as I told you, is I1 minus I2. With that, we have got the contribution of what? 12 milliamperes or 2 milliamperes, 4 milliamperes equal to this. Understand that? Fine. So let's move on to the next problem now. So see, this is what superposition theorem is. Step 3, you need to be adding. I naught 1 we found out, I naught 2 we found out. This is negative, this is positive. So the algebraic sum is 0.5. So I naught is 0.5. But if you take the individual responses, they are this. This is individual response of 6 volts. This is individual response of 4 milliamperes. So algebraically add them together to get to the final answer. So this is what superposition theorem is. Okay with that? Yeah. The next problem is this. In the last problem, we found out the current. Now we have to find out the voltage across 2 kilo ohms. Again, this problem can be solved by mesh analysis, node analysis, but they have asked us to solve this by superposition theorem. Now, this V naught is sum of how many individual contributions? This V naught is sum of how many individual contributions? It is sum of 3 individual contributions, because there are 3 independent sources. So this will take more time because you have to find 3 voltages and add them up at the end. Get that point? Okay. So how do we represent V naught? V naught we represent as V naught 1, V naught 2, V naught 3. Let's say V naught 1 is the contribution of 12 volts, V naught 2 is the contribution of 6 volts, and V naught 3 is the contribution of 2 milliamperes. Okay, so let's take when we are seeing V naught 1, when we are obtaining V naught 1, okay, 6 volts and 2 milliamperes have to be deactivated. There should be only one source acting at a time. The other sources have to be deactivated. And when you are finding out V naught 2, keep 6 volts active, deactivate 12 volts and 2 milliamperes. Similarly, when we are finding out V naught 3, 2 milliamperes is active, the other two sources are inactive. This is how the things go. Is this okay with you? Now, to find V naught 1 is step 1. Okay, so deactivate 6 volts and 2 milliamperes. You need to have your circuits in place. Okay, so see the circuit. What is this? Is the contribution. This is the contribution of, that's why you have to write. This is the contribution of 12 volts. So the other two sources have to be deactivated. See, this is how it looks like. Here was the current source, which is open circuited. Here was the what? Voltage source, which is short circuited. So we only have 12 volts acting now. So what we obtain is V naught 1, and that V naught would be contribution of 12 volts when it is acting alone. Get that point? Now we have to find V naught 1. Earlier the circuit was consisting of what? V naught. Where is V naught? V naught is here. So now this V naught would be coming as V naught 1. Fine. Okay. Now what? Yeah. What do you use? You don't go for combining these two because these two are in series. But if you do that, you can combine, not that you should not. Actually, these two you cannot combine though they are in series, because we have V naught 1. And where is V naught 1 dropping? It is dropping across 2 kilo ohms. If you combine these two, you lose V naught 1. And where will you find V naught 1 if you lose? So that is common sense. Okay, use that common sense. Okay, and see when we should be combining the resistors and when we should not combine the resistors. Understand that? In the first problem we had that case, right? So I told you we can combine, but we didn't, right? Let's see why maybe such a case is there. Where is I naught 1? Okay, I naught 1 is here, whereas you can take these two in series combination, then bring that in parallel with this. So absolutely you can go for reducing the size of this. Okay, but here you cannot. Where here you cannot combine these two. If you combine, we are losing V naught 1. Fine. So let's mark the two currents, IA, IB. Okay. Find out how we can do that. Go with IA, go with mesh 2, because we are not, if you apply, see here, if you apply KVL to mesh 1, anyways, IB will not come into picture at all. See, IB will not be a part of the KVL that is applied to mesh 1. So we can directly apply KVL to mesh 2. So these are all something that you can think of to save time. So if you apply KVL to mesh 1, down the line you will understand that is not needed. But if you observe it properly, you will understand that, okay, there is no need of applying KVL to mesh 1, because that KVL will not contain IB. Why is IB needed? Why IA is not needed? Because to find out VO1, IB is needed. IA is not at all necessary. So that's why we are applying KVL to mesh 2. Okay, so apply that, find out IB. IB is happening to be 0. Okay, no problem. IB is happening to be 0. So which means that your VO1, which is minus 2K into IB. Why it is minus 2K into IB? Anybody would you like to comment on that? Why I have written V01 as minus 2K IB? Anybody? Give me some inputs. Nobody wants to talk. Okay, why I've brought this minus sign here is because this IB, okay, is approaching the negative sign of VO1. So that's why I've brought that here. Okay, but since IB is 0, VO1 would also get 0. Fine. Now we have to find VO2. So we have to be deactivating 12 volts and 2 milliamperes. That is done here. Okay. So this 2 milliamperes is deactivated, and here was your 12 volts, that is short circuited. Fine. Again, find out VO2 by marking different. And see here I marked IA, IB. Okay. Here I am marking IX, IY just to avoid the confusion. Fine. So if we do that, uh, mesh 2 again, because again Ix will not be required to find out V02. So apply KVL to mesh 2 only. Find out IY. After finding out IY, okay, what is V02? V02 is what? Minus 2K into IY. Minus 2K into IY. That's why it's becoming plus 3 now. Everybody understand? So if you don't consider minus here, you will get this minus 3, and at the end when you add, you will end up getting a wrong answer. So that's why you have to be little careful when you're writing the voltage. Since this IY is approaching the negative sign of VO2, so that negative sign needs to be reflected here. Fine. So VO2 we have found out. Let's see how we can find out VO3 by deactivating 12 volt and 6 volts. So 12 volts was here, that is short circuited. 6 volts was here, that is also short circuited. 2 milliamperes is what we are having to find out VO3. So VO3 is the contribution of 2 milliamperes when it is acting alone. The other with other two deactivated. Okay. So what you will do? Oh, something happened here. What is done? See, this 2K and this 2K are in parallel. Everybody understand that point? How they are in parallel? See, this point and this point are same. These 2 points are same. Everybody understand that? See here, this point and this point. You should. I hope you are able to see the pointer that I'm moving on screen. Okay. So these 2 points are same. So bring this point here. See, 2K ohm, 2K ohm are in parallel. So 2K, 2K in parallel would give you 1K. Understand that? And that where would that 1K be? 1K would be here, not here, because this point you can bring here, but this resistor you cannot bring here. Everybody understand that point? So these are all small adjustments. There is no need that you should do this. You can mark 3 mesh currents and find out VO3. But to save time, we can look for such adjustments. We can adjust the 2K 2K parallel to get one resistor, that is 1 kilo ohm in this case. Okay, now how many KVL problem it would be? It would just be one KVL problem because we know the current here. So mesh analysis. Oh, or beautifully done. See here, what's happening? If there is a resistor in series with the current source, this resistor is redundant. This is of no use to me. So there are 2 resistors in parallel. So this current comes at this point, gets divided into 2 parts. So that means it's a current division rule. So using current division rule, what we can do? What is important here? I2 is important or I1 is important? This current or this current? I1 is important. What is I1? I1 is the total current entering this particular point into resistance of the other branch divided by sum of the resistances. And what is another way of looking at it? Still beautifully done. Since both the resistors are same, the division would also be equal. So 2 milliamperes comes here. Since both these are same, that will get divided into two equal parts. That means two equal parts means what? 1 milli goes here, 1 milli goes here, and again comes back as 2 milliamperes. So it is 1 milliampere. So what is VO3 now? I1 is approaching positive sign of VO3, mind you. So what is I1 now? I1 is, sorry, what is VO3 now? VO3 is 2K into I1. There is no minus now because I1 is approaching positive sign, which happens to be 2 volts. I1 is 1 milli. So 1 milli into 2K. 1 milli into 2K would give you 2. So it's 2 volts. Everybody understand that point? So that is what we have done here. By superposition theorem, we've got 3 voltages and 3 voltages can be found out like this. Those who have not given the attendance can give. Okay. I'm going to solve another problem. Fine. That's the problem wherein the dependent source is involved. What we should be doing with the dependent source is what we are going to learn. Fine. See, there are two independent sources. This is sufficient for superposition theorem. But if there is one independent source and one dependent source, no, there should be multiple independent sources. Okay. So I would be sum of how many individual contributions? This I would be sum of two individual contributions. One contribution of this. Okay. Another is contribution of this when the other one is not acting. So this I1 is contribution of this, I2 is contribution of this. Okay, the dependent source, what do we do with dependent source? Don't do anything. Okay, we cannot deactivate it, keep it as it is and find out. See, we have just kept it as it is. The current source is open circuited. Find I1. Understand that? Okay, and one other thing, very important thing that we have to express is this. See, when I is flowing, this voltage is depending on current I. So this is I. So when I remove this I would become I1. Okay. So this is I, this is I. Now, when that current source is removed, this will become I1. Earlier, this was depending on I, but now it has to depend on I1. Everybody understand? So this is what you need to be very careful about when you are dealing with the dependent source in superposition theorem. So earlier this was 3I. Now it has to be 3I1 because I has become I1 now. Is everybody okay with this? What I mean is this. Earlier, it is depending on current I when both the sources are acting together. But now when you remove this I is I1. So when this I is I1, this I should also become I1 is what I'm saying. So that is the way we are finding out I1 by applying KVL, which is 3 amperes. Okay, we have to find out I2 by deactivating 24 volts. So that is short circuit. Find out I2. So when this becomes I2, this current should also become I2. Earlier it was 3I when both were acting. When this voltage source was acting, it was 3I1. When the current source is acting, it is 3I2 because this I has become I2. Is that okay with you, everybody? Fine. So find out I2, super mesh problem. Okay. Mark two currents, write the constraint equation and apply KVL to super mesh. Get this point? Now, what is not good in this? 3I2 is there. When we are writing the mesh analysis equation, KVL in mesh analysis, the equation should only consist of the mesh currents, but I2 is not a mesh current, but we know what is this in terms of mesh current. So I2 is IX. Substitute I2 as IX and get one equation. Okay, and another equation is here. So solve these two equations to get IX and IY, and I2 would be your IX. So these two we have found out. Okay, and I2 would be your IX, which is minus 0.75. Now you have to add I1 and I2 to get to this answer. Is this okay with you? Okay, I'm rushing through, but I'm giving you the concept. Rest is your mesh analysis and node analysis. Nowhere we have used node analysis till now. Okay, you can even use node analysis, but that does not mean that you have to forcefully use node analysis. No, whichever seems suitable is what you should go for, but you have the freedom to use any method you want. Get that? For example, see here in this problem, in this case, where was the previous problem? Maybe, yeah. In the previous problem, we thought of mesh analysis. We thought of no, it's not. Mesh analysis is also not needed. Node analysis is also not needed. Source transformation is also not needed. Current division rule is sufficient. And even by current division rule, we didn't go for writing the equation for current division. Okay, if you write also, you'll get the same, but that is not actually needed if you observe it properly. Both are the same resistors. This current has to get divided into two equal parts. What is two equal parts? 1 milli here, 1 milli here. Okay, so that is smart way of looking at things. Everybody understand that point? Okay, so we have solved three problems. Look at these problems. Okay, you can solve any problem of this sort. Fine.